coming down like that. There can be multiple piles, right? So there's a column, and this column will have a load transfer through these piles, right? So therefore, the important thing is, so once you do the connection here, can you tell me the important thing at site? If you are a site engineer, what you will look for? In analysis, if I assume to be fixed here or a hinged here, you have to make sure that you do a connection which is compatible with what your assumptions are. Because the reactions what you will get will be function of the boundary condition. If you assume it to be fixed and you go apply the loads based on fixity, that is something else. If you assume the moment, something else. So typically what it is done, a pile cap, the column bars will come down, go like that. The column bars has to come down, have a lap length there. The pile reinforcement has to go up as well. So if you want to have fixity, you have to do all the detailing like that. So the column reinforcement has to go up. That's been made sure, right? So they are the reinforcements. So the column reinforcement, say the column looks like this. You have got reinforcements like that. So these reinforcements has to come down all the way to the pile cap to have the connection based on what you have assumed in analysis. Okay. So that's an example of this. And can you give me an example of this? A case? A bridge pier, yeah. A large bridge, you know. Okay, now, what are the applications of these? Where do you need pile foundations? Some examples. Where you would definitely need pile foundations, so that there's no other way. Bridges? Yeah, maybe a big bridge, a major bridge, like a cable-stayed bridge. You know, like a large span bridge. You can't avoid. You have to have it. Yeah. Yeah, highest building. Yeah, in most places you have to have a sort of, yeah.
Offshore applications.
Offshore applications, yes. So that there's no sort of other way to do it, right? Okay, that is right. So the applications are offshore. Now, bridge foundations, port structures. If you have a port structure, so you have to go for a pile foundation, isn't it? Because you really can't. So normally, underwater, you normally use a pile foundation steel. So you hammer it down there, right? Because it's quite hard to have concrete there. Now, each of the applications are governed by different codes of practice. So a same pile foundation, if you use an offshore application, there's offshore codes like API, ISO, DNV, there are codes like that, right? So the pile foundation, if you are doing a application offshore, you use API code of practice. If you use a bridge foundation, there are bridge codes, right? There are bridge codes out there. If you go for a building and the buildings, you use Eurocode 7, right? And port, so each has different codes. But however, so in a class, so you can't teach every code. So what I will do, I will try to give you the fundamentals of pile foundation. So what are the important things? What is the theory behind that? And then you will see all codes are more or less same, the same principles. However, all codes are more or less calibrated for the application. That means, if you look at API code of practice, they are calibrated towards the offshore piling. So they have, all codes are mostly calibrated. So they have got lots of huge applications, database. Based on that, they have got some empirical formulas, and it works well in that application. So we normally don't use API code to do something else, or you won't use a Euro code to do something else, because they are mostly calibrated in that particular way. Okay. To give you an example, what I have done, I have also in London, if you are doing a pile design, there's a guidelines document from London Survey Association. So I will give you that particular guidelines to just to show that all are different, right? But the fundamental things are more or less same. Okay. Is there any question so far? Is there any question so far? Awesome. Yes. Yes. Euro 7 and what else? Euro 7. Euro. Oh, yes, but we are bringing the. Well, we are doing Euro 7. That's only for function general. So still in our structure notes. So we normally don't get. We don't need to do it. We normally have enough to the Euro 7. So we don't need. Okay. Now, here's an example of a caisson formation. So what you can see here, that's a major bridge. The bridge width is 1.7 kilometers. Huge flow. So in those sort of areas, so you can see here's a mighty river. It's a huge flow. So here the pile, etc. will have so much scour, so they can't use piles. So in this case, they will use caissons to support that one. And actually, this sort of area, if you do a bridge, you do for a double decker. So you do for a railway and a roadway bridge. So you can make it optimum. Because the most cost goes on the foundation. So if you do it big, then you can use it for both purposes. So the sort of road and a rail bridge. Okay, so here's one of my example. And what sort of shapes they can take. So often, if that particular had this sort of shape, the one what I showed you before, this particular bridge had if you see here, it has a double D type of shape. And the typical reasons are, if you have one large caisson, like a 12-meter diameter, look at diameter, 12-meter diameter, quite a large thing. So if you have a single track railway, so you can put one. If you have a double track, you can either do a 2 circular, or you can go for double D. Do you know the advantage here? Do you know the advantage here?
Keeps the water out of the space.
Yes. So keep the volume down a bit. That would be okay. So here what you can see is that as the flow goes there, you can get a form of wake here. So this is a scouring. So what happens? These are mighty rivers, large rivers. So there's huge flow, huge amount of flow. So those flow can actually cause scouring action there. If you have 2 caissons, so the scouring will be lot larger. Then you go and do some rock dumping to avoid the effects of that. In that case, if you have a double D, it sort of helps you to mitigate that, right? So in this case, you may have a lower cost to install because less amount of concrete, but you will have perpetual cost, operational cost, maintenance cost to keep it in action. If you do that, you have a higher capex cost, means a higher cost to install it. But once done, you are more or less good for many years. So lower maintenance cost. Okay? And also, if you see in this particular way, the large sections, so it will easily take quite a bit of eccentricity of loads. And if you have it here, you have to make them compatible, right? Okay, so these are the different types of caissons. And for that particular example, bridge, what I was showing before, so what you can see here is the bridge is 1.3 kilometer wide, and you can see the spacing of the foundations are around 123 meter. And what you can see here, the foundations is 41 meter below water level. And the diameter, the double D shape is 16.4 meter by 10 meter. Massive thing, right? The reason is that this is a seismic zone, very high seismic zone. So the topsoil might liquefy. So on an earthquake, you will have a lower amount of embankment. So you have to make the foundation a bit more deeper so as to take into account the extreme loads. Yeah. So when you do the foundation, you have to look into the different aspects, because if you're doing a bridge like this, so you got to do it for a good 100 years or even more, right? And in the 100 years, there can be multiple earthquakes. And make sure that on earthquakes they will operate. Yeah? Is there a question so far? And what you can also see, that to do a design, what you would need to know is a ground profile. Right? You also have to know the ground profile in order to do any calculations. Now, if you look into these sort of foundations, what would you consider? What are the things to consider for design? If you do the foundation design for these sort of bridges, what would you look for? Thinking back the flow chart, what I was showing in lecture 1, look for some loads, yeah? First is the load, ULS, ultimate limit state. So what is the maximum load will be applied to your structure? What would you consider for this bridge? Railway load. So I think you can also look into the maximum load that bridge will carry. The sort of heaviest vehicle it will go through. Often military tankers are a design consideration. So you're taking into account the tanker, the large load that will go through, right? Accidental loads, yeah. Yeah. So they may impact, yeah. So you have to find out the ultimate maximum vertical load. So this is what I am doing here is first is to know the maximum vertical load, lateral load, moment load. So VMH, maximum vertical, lateral, and moment. Right? Second is deformation. How much would you allow deformation? Right? What happens if it deforms? What happens? Say on an earthquake, it deforms a bit. What might happen? Okay, so say on an earthquake load, you get a big shaking. So the ground liquefies to a certain depth. You get shaking. You think a little bit deforms. It follows the fall of the pier. So the bridge deck will fall off, isn't it? Yeah? So what you might find that this bridge little bit inclines or bends. If it bends, so the bearing, the deck will follow the bearing. Yeah? So what you do, you got to estimate what is the deformation under the extreme load, right? So once you know the deformation, you can then build your pier cap, the pier cap with a bearing such that it will not come off the pier cap. Is it clear? So what I mean to say, let me show you by a diagram. So that is your, so that's a bridge pier. You may have here a bit of hunch, and then you put here a pier cap. That's your pile cap here, and you put your piles down there. And here you put your bearings, and on the bearings you put the sort of girder. That's the bearing, and you put the girders there. The girders will be there, and on the girders you will put down the deck. Yeah. So you have got, this is the bearing. You put the girders, the big beams on these bearings, and then you put down the deck at the top, the bridge deck, right? Now if this deforms more, so it will happen is that if it deforms more, it will fall off. So what you must do, find out the maximum deformation of the top deck so that you can extend this a lot more that it doesn't fall off. Right? Dynamics. What is important? Dynamics. Yeah. So the as the sort of moving load, so there will be a resonance. There can be resonance. Right? So how will you take into account in your design? So if you're doing a design, what would you calculate?
The natural frequency structure.
So, to calculate the frequency, what you would need? You would need the foundation stiffness, isn't it? To calculate the frequency, what you would need is the foundation stiffness. What do you mean by stiffness? Yeah. So stiffness means the sort of, you want to know moment versus theta. So of the foundation, what moment will give you how much rotation? Or you might want to know lateral load versus displacement. That will give you, this will give you the K rotational or K theta, and this will give you K lateral. Yeah? So these are required for a foundation to calculate the dynamic characteristics. Okay. And then extreme loads are earthquakes. Extreme loads, earthquakes, hurricane, floods or whatever. Accidental loads can be ship impact or other accidental loads, right? And anything else, there can be other loads which are obviously function of that particular site. It may not be every applicable. In some places, it can be applicable. So, exactly what we discussed just before. So, one of the important part of a bridge is the dynamics part, right? So, if you choose a foundation, if you choose a particular foundation, you can find out the stiffness, A smaller pile, a smaller caisson will have a small stiffness. A bigger pile, a bigger caisson will have a large stiffness. Also, a small pile in a stiff soil will have high stiffness. Right? So, do you know how to calculate these stiffnesses of foundations? Do you know? Okay. Something new for everybody. That's good. You know about pile design, so I think I was thinking, what's new for you? It's going to be new for you, isn't it? Of course, but final element will be expensive because you, for any pile design, you need to do a 3D final element. And 3D final element is not used for routine things. It's very expensive. The software costs £50,000 per license, and then you need somebody expert to run those final element. You know, so it's not that easy to work on that. So we will learn about how can you find out stiffness of foundations, and then if you have a model like that, you can easily work out the different things. Yeah. So there are different ways of doing it, but Eurocode 8 gives you some equations for stiffness of foundations. So what it needs a ground profile. What it needs is how does the ground stiffness change with depth. So it basically says three types of ground. One is uniform ground stiffness, another is linearly varying with depth, and third is parabolic. Can somebody tell me where we can expect this sort of ground, uniform? Over-consolidated soil. So if it is a over-consolidated soil, where can you get that soil? Over-consolidated soil?
Brownfield soil.
Brownfield soil, yeah. So or some parts of North Sea, because there was huge ice loading, ice age, huge pressure was there, ice melted, so it's now very deeply OCR clay. London sometimes is a OCR clay because they often say that there was a huge amount of construction done, right? Yes? No. What about this one? Linear variation with depth. Normally consolidated soil. So normally consolidated clay will have a ground profile like that, and sandy soil is roughly parabolic. Okay, so what you can do to use these equations, so if you have a ground profile, you have SPT values or CPT or whatever, and then you can check how is the soil stiffness changing with depth, and you fit into one of these types, right? And then you can use Eurocode formulas to find out the stiffness values, right? This you will learn in the course of these things. So here's an example. So what you can see here, it says ground profile, homogeneous, linear, parabolic, gives the equations for the different values of stiffness. Yeah? Now, by the way, you ask me, what is this KMH? What is KHH? Lateral stiffness, yeah? That means if I apply 1 unit of load, what is the deflection? So this means, right, I apply the load, lateral load, what is the deflection? ML is the moment. I apply a moment, what is the rotation? KV is the vertical. I apply the vertical load, what is the settlement? Right? The linear part. What is this one? KMH? What does combined mean? What does it mean? Resultant. What does it mean? Resultant mean? Okay. It is important to sort of. Okay, so what it means is, if you have a cantilever beam, if I apply a point load there, so this would deform like that, isn't it? Yeah? So, I know this delta. This delta is given by anybody? Anybody can tell me this? Right? Now, if I want to work out the stiffness of this cantilever column, what does it mean? Stiffness means load required for unit deflection. So when delta is equal to 1 unit, say meter, what is P is the stiffness. Yeah? So therefore when delta is 1, P is given by 3 EI by L cubed. Right? Therefore, the stiffness is given by K lateral, or HH term is there, is basically 3 EI by L cube. Yeah? Yeah, we used this thing before, isn't it? Right? However, you also get here a rotation, isn't it? You also get an angle there. Right? You also get an angle there. So this lateral load also gives an angle. Right? And that's the coupling term. So what I will explain to you what does it mean here. Say that's the foundation. That is a foundation, and the foundation has got a moment and lateral load H, yeah? So you have got moment M and a load H. And you want to know what is the rotation and deflection. Yeah? Because a lateral load gives you both. If I apply a moment, also give me both. Now, this matrix, this is a 2 by 1 matrix, yeah? That's a 2 by 1 matrix. This is 2 by 1 matrix. This must be 2 by 2 matrix. Otherwise, you cannot multiply them. Right? This 2 by 2 matrix. So this one is K rotational. So if I now do the metric operation, so I will write here K MM and this will be the coupling term. So, if I now split the whole equation, I get M is equal to KMM theta plus KMH delta. So, moment will give you rotation, but also then there's a term due to deflection. That's the coupling term. Okay? Is it clear? That is basically the compatibility of load deflection. Yeah? So it's the compatibility of load to the deformation. So KMH is basically that's the sort of coupling term.
Yeah. And that's the second one.
Yeah, so basically if you look into moment, will be normally rotational spring times theta. But then you have the coupling term, and second will be KMH.
Yeah.
That's a coupling term. If you look into codes of practice, they have a coupling term, and here's the meaning, what does it mean? Yeah? Yeah. Because this thing also gives rotation. So if you just say, just see P and theta, that will be the coupling term. And if you apply a moment, you get rotation and also diffraction. So if you link the moment to the diffraction of the diffraction. Here, moment So, going back to that, so you need to estimate, when you're doing a foundation design, you need to estimate those numbers. Once you choose a foundation, once you choose the foundation and know your ground, you can find out those numbers. What are your stiffness terms? And based on those stiffness terms, you can then check what is deformation, right? For example, can somebody tell me what is critical in this design part? The lateral load. Okay, the lateral load. Lateral load will come from where? It will come from, say for example, a train is passing through, a big large train, a windy condition, a big wind load acts on the train, that has to be taken by there, right? A big long train, the whole wind load, right, on that whole surface. Think about this condition. This one is 123 meter span, yeah? So you have a condition where you put the deck on one side and the other side has got no deck. So when you are trying to install the bridge deck, there can be a condition that there's only deck on one side. When you're having the other one launched, there will be large movement, isn't it? Because you have a load on one side. Yeah? Then you must check under that condition how much will it deform. Right? So you got to think about all these steps, how you will construct a whole bridge. Yeah? Isn't it? Okay, so this is one. Okay. Now, to apply this formulation, what you would need in the Eurocode way to do it, you need two numbers, two things. One is the variation. So you choose a particular variation, and then you need to know the ground stiffness at one diameter below. So Z by D is the depth normalized by the diameter. So Z by D of 1 means at one diameter below. That means if your pile diameter is 5 meter, this means this is 5 meter. And E by ES of 1 means to find out the stiffness at one diameter below the depth. So you only need that parameter. And then you can use these Eurocode formulas to work out these three terms. So you can see the HH value, ML, MH. And you can get for a pile foundation these numbers. And once you get the numbers, then you can use it. Once you know the loads acting on your foundation, you can use these numbers to work out the deformation. Yeah? Okay?
What's EPADS?
Okay. So they are pile soil stiffness ratio. So this will tell you, this ratio will tell you how stiff the pile is compared to the soil. That means if a pile is in a soft clay, soft soil, this will be a very high number. The pile is in a very stiff ground, that will be a low number. Yeah? And that's why, if you see, it's called flexible pile formation, numbers for flexible pile. That means they can deform. Yes? When we'll apply these equations, things will get more clear how to apply them. Yeah? So, here's a bridge and pile formation. So you can see that the deck fell, right? These things do happen. Right? Here are other examples of bridge and pile. So you can see the middle, few spans fell. Again, the deck fell. And one of the important why it happens is why the middle part only fails, because if you are having a pile formation in a river, what happens is, so you can see that here the piles are a lot more, you have a long unsupported length. Typically in a bridge design, you put the pile to a similar length, because if you are doing a project, you normally order same pile length for the whole site. You don't say smaller or bigger, because it's quite simple to drive the whole thing. And what